In this lesson, we're going to learn about antiderivatives. And here we're attempting to discover a process that will allow us to reverse the process of differentiation. Because in all of mathematics, for any operation that we can perform, we also like to find an operation that would undo that particular operation. So for instance, addition has subtraction, multiplication has division, exponentials have logarithms, and so forth. But in this case, we're given the derivative of a function, and we want to determine the function for which the derivative came from. This is the process of finding an antiderivative. Definition: a function capital F is called an antiderivative of lowercase f if the derivative of capital F is equal to lowercase f. Perhaps that will make a little bit more sense in an example. So for instance, if lowercase f is 4x to the third power, then capital F of x equals x to the fourth power is an antiderivative of f, because if we took the derivative of capital F, so we took the derivative of x to the fourth power, we would bring the exponent down, subtract by 1. So that would be 4x to the third power, which is equal to the lowercase f that I originally defined. So capital F of x is an antiderivative of lowercase f. But note that antiderivatives are not necessarily unique, but you would never have another function that had like different powers on x or any added other pieces of the function. The only difference is you could have is an added constant. So for instance, capital F of x being x to the fourth plus 5, that would also have a derivative of 4x cubed, as well as x to the fourth minus 2. If you took the derivative of that, it would also be 4x cubed, and even x to the fourth minus a half. These all qualify as valid antiderivatives of the function f, because when you differentiate them, you get 4x to the third power. And the reason is, when you take the derivative of a constant, you get 0. So that's what happens here. But that lends us to a definition here. We correct for this issue by adding an arbitrary constant to our antiderivatives, which gives us a general solution to the antiderivative. So the general solution, so all of the antiderivatives of lowercase f will all look like capital F of x equals x to the fourth power plus some constant. The notation for antiderivatives looks like an elongated s, and there's reason for that, which we will discuss as we get further in the class. But just know that when you see this symbol, you're being asked to find an antiderivative. So for example, from the previous slide, capital F of x is equal to the antiderivative of 4x cubed dx. And that operation results in x to the fourth power plus c. So just so you know, the process of finding an antiderivative is also called integration, and often we use these terms interchangeably, so just know that you can hear either one and it means the same thing. And also note the notation of the dx term. Where that comes from is the differential form of a derivative. So for instance, if you have dy dx equals f prime of x, then what that implies is dy is equal to f prime of x times dx. That's the differential form of that derivative. Now, when you solve for your antiderivative, you would do the antiderivative of a derivative function, dx. And that dx actually tells us what variable the derivative was found with respect to. So we know what variable to go back to. So it's an important piece, but it's often overlooked. But it definitely needs to be a part of all of your antiderivatives when you write them. Now let's look at some antiderivative rules here, which will help us learn how to effectively evaluate some antiderivatives. The first is the simplest rule. The antiderivative of 0 is equal to the constant c. All of these rules are effectively inverses of derivative rules that we've had. So if you reversed this and said, okay, the derivative with respect to x of the constant c, well, we know that that's going to be 0. So the inverse of that says that the antiderivative of 0 has to be c. Next up, the antiderivative of dx is equal to x plus c. And again, you can show this through differentiation. So the derivative of x plus c is going to be the derivative of x. We know that is just 1. And the derivative of the constant c is 0. So we end up with the constant 1. And that's all that's sitting right here in the inside the integral. In number 3, we have the antiderivative of the constant k times dx is equal to k times x plus c. So effectively, it just means if you have a constant, then you multiply x by that constant. But in fact, that's actually part of a more generalized rule in that if you have a constant multiplying any function, you can actually just take that out of the operation of antiderivatives altogether and find the antiderivative of the resulting function, which shouldn't be much of a surprise because we could do the same thing with derivatives as well. And since these are the inverses of derivatives, it should make sense that you can do this. Similarly, if you have the sum or difference of a bunch of different terms inside a polynomial, for instance, and you wanted to find the antiderivative of each one of those terms, that's perfectly fine. You can do polynomial terms added separately. This one is probably the one that you'll use the most. This is the inverse of the power rule for differentiation. So the power rule for differentiation said to bring your exponent down and make it a multiplier, then subtract 1 from your exponent. The inverse process is to add 1 to your exponent and divide by the new exponent. And that's exactly what the inverse, the antiderivative rule says here. And again, we can show it pretty easily. If we took the derivative of x to the n plus 1 over n plus 1, then the derivative of this would say to bring your exponent down, so bring the n plus 1 down, and subtract 1 from it. So n plus 1 minus 1 would just be n. So these would cancel, and you'd just be left with x to the nth power. So this works out through, again, the inverse of a derivative. Next, the sine of x is equal to the sine of x. Now, this is the inverse of the sine and cosine rule for derivatives, which was really nice because these were derivatives of each other, basically. But if you did the derivative of cosine, it resulted in negative sine. The inverse rules here for the antiderivatives, the signs are the opposite. So the antiderivative of cosine is positive sine, whereas the antiderivative of sine is negative cosine. So they're still antiderivatives of one another, but just pay attention to those positive and negative signs because that can throw things off. Next up, we have the antiderivative of secant squared dx is equal to tangent x. And notice that this isn't the antiderivative of just secant x. And the reason for that is we didn't have a rule for differentiation that resulted in just secant x. We had the rule for the derivative of tangent was secant squared, And so therefore this is the inverse of that differentiation rule. So like I said, all of these are inverses of differentiation rule. Similarly, secant x tangent x, if we did the derivative of secant, that's what we would result with. So it should make sense that the antiderivative of secant x tangent x gives us secant. The next two are just the partner functions of those. So let's jump down here to 13. The antiderivative of e to the x dx is equal to e to the x plus c. And that should make sense because e to the x was its own derivative, so it's also its own antiderivative. Lastly, we have our logarithmic rule. And what we learned from differentiation is the derivative of the natural log of x was 1 over x. And therefore, the antiderivative of 1 over x is going to be the natural log of x. Now, notice there is a set of absolute value bars in the natural log. This is important because you can't take the natural log of a negative number, and because the function 1 over x could be positive or negative, you can't really determine if the original value of x was positive or negative. So to make sure you get a valid antiderivative, we take the absolute value of x. Also, it's tempting to try and use the power rule for this 1 over x dx. So for instance, you can write 1 over x dx as x to the negative first power, but the problem there is if you try to use the power rule on this, you would do x to the negative power, which is 0, divided by the new power, which is 0. And this division by 0 doesn't make sense. So this isn't how we will go about integrating 1 over x. It will always result in a natural logarithm. All right, let's see some examples and learn this process. A 6x dx, we want to find its antiderivative. So the first thing that I notice is that there is a constant multiplier on the inside of this antiderivative that I can pull out. And when you start learning these, you'll probably want to do these kinds of things to kind of help you out. Make the problem look less intimidating by removing things that aren't necessary. Right? The antiderivative of x dx, we can find that through the power rule. So the power rule says to take the x, raise it, increase the exponent by 1. So we have x to the first to begin with. So now it's going to be x squared, and divide by the new exponent. And you always want to simplify these because generally there isn't going to be a lot of simplification that's required for antiderivatives. So just go ahead and do it. It's usually just manipulating constants. B, the antiderivative of 1 over x squared dx. So the power rule is probably the rule that you'll use the most. And so you want to be able to see all the different ways that you can use the power rule. And here's one where you can take exponent in the denominator and rewrite it as a negative exponent. Now we couldn't do that when it was just 1 over x. That results in the natural log. But this is okay because when I use the power rule here, x to the negative 2 becomes x to the negative 1 because I increase my exponent by 1, divide by the new exponent. I don't have division by 0 here, so everything's fine. So 1 over x plus c. 4 times the square root of x. This is another place where the power rule can be used. It will be 4 times the antiderivative of x to the 1/2 power instead. And that's going to be helpful here because now the 4 I can leave alone. The 1/2 power, what I'll do is increase it by 1. So that would be 1/2 plus 1 is 3/2, divide by that new exponent, tack on a plus c, and then just do the small amount of simplification that you can. So this would be 4 times 2/3 x to the 3/2 plus c. 4 times 2 is 8, so this is 8/3 x to the 3/2 plus c. D, the antiderivative of 6 cosine x dx. 6 is a constant multiplier that can be removed, and then I'm left with the antiderivative of cosine x dx. So the antiderivative of cosine x dx, just the way I think about these to remember the signs is that I know for a fact that the derivative of cosine is negative. So then I just use that fact to work my way around the others. So if the derivative of cosine is negative, the antiderivative is positive. So this will be 6 times the positive sine of x plus c. Here's another one. This time we have a polynomial. It's got multiple terms, and you can split these up into separate integrals. So for instance, I could write this as 3 times the integral of x dx minus 4 times the integral of dx. And separately, these integrals aren't difficult to come up with. We would just use the power rule effectively on each one. So I would have 3 times x squared over 2, just increasing the exponent by 1, dividing by the new exponent, minus 4 times inside this antiderivative is a 1. So when I integrate 1 dx, that becomes x. Then I have a plus c. Or in the end, this will become, let's say, 3/2 x squared minus 4x plus c. Now, I want to mention one other thing about this integral dx. You really can use the power rule to show this, that this is true. So for instance, if you consider the constant 1, because effectively I'm integrating 1 dx, you can think of the constant 1 as x to the 0th power dx, because anything to the 0th power is in fact 1. Now, if you use the power rule, you can increase your exponent by 1, so x to the 0th plus 1 would be x to the 1st. Then divide by the new exponent, tack on a plus c. So there you have it. So that proves that the integral of just dx is x. All right, next up, the antiderivative of 3 sine x minus 2e to the x dx. This is going to be first written as the integral of 3 times the antiderivative of sine x minus, be careful here, I don't want to miss a dx in there, minus 2 times the antiderivative of e to the x dx. And so all I'm doing now is just finding the antiderivative of sine x dx and e to the x dx separately. Alright, so the antiderivative of sine x. The derivative of cosine is negative, which means that the derivative of sine is positive. And the integral of sine then would be the opposite, so the integral of sine would be negative. However you choose to remember those, go with it. I have my ways that work. Pick a method that works for you. This then would be negative 3 cosine x minus 2. The nice thing about e to the x is that it's its own antiderivative. So it's just going to be minus 2 e to the x plus c. All right. Next up, the antiderivative of t plus 1 quantity squared dt. Notice we have a different variable, but we're integrating with respect to a different variable, so that's okay. But we don't have an inverse of the chain rule. So we can't find the antiderivative of this function as it sits, but if you can go through and manipulate it algebraically, then you can probably rewrite it some way that you could actually find the antiderivative. So for instance, the quantity t plus 1 squared is t squared plus 2t plus 1 dt. And now this is a polynomial, and I can find the antiderivative term by term. And instead of splitting this up into 3 separate antiderivatives, I'm just going to go through one by one. So this would be t to the third over 3 plus 2 times t squared over 2 plus t, and then still plus an arbitrary constant. And the only thing to do in the end is just simplify any constants that you have here. So I'll express this 1/3 t to the third power. These 2's are canceling, so that's just plus t squared plus t and plus c. Next up, the antiderivative of x cubed plus 2 divided by x squared. Here, what we can do is, again, manipulate this algebraically. I have a polynomial divided by a monomial, and you can simplify that by taking each, I guess I should bring that plus down a little bit, taking each of the terms of the polynomial in the numerator and dividing them by the monomial in the denominator. So this makes my function look more like, so x to the third power over x squared is just x. 2 over x squared I can rewrite as 2x to the negative second. Both of these particular terms can be integrated using the power rule. So I would have x squared over 2 plus 2 times, so x to the negative second, if I add 1 to that, it will be x to the negative first divided by negative 1. So looks like I'll have 1/2 x squared minus 2 over x plus c when I simplify everything. Antiderivative of 5 over x. So this one, it is very tempting to try and use the power rule, but as I showed with earlier, if you try to use the power rule on 1 over x, you end up with x to the 0 over 0, which doesn't make any sense. So know that this is your natural log. So this will result in 5 times the natural log of the absolute value of x plus c. And that's it for this one. Alright, the next thing we need to talk about are general solutions versus particular solutions. So in the first slide, I indicated to you that when you find your antiderivative, that there are other functions that are antiderivatives, but all off by an arbitrary constant c. When you add that arbitrary constant c into your solution, you have a general solution. So you have all the antiderivatives for that particular function. Now, if you happen to know an original point that existed on the curve of the original function, you can find the one antiderivative of all of those possibilities that passes through that point, and that will give you a particular solution to the problem. So in order to find a particular solution, you have to know the point that exists on the original graph, and you can solve for it. And I'll show you how that's done, but let's pull up an app to help visualize this. So I have a function f of x is x squared plus x. Now, if you look at the curves over here that are plotted, this is not the plot of x squared plus x. In fact, it's the antiderivatives. So if I said capital F of x is defined as the antiderivative of f of x dx, then this is going to be the antiderivative of x squared plus x dx, or 1/3 x cubed plus 1/2 x squared plus c. So what you're looking at is each one of these curves is the graph of 1/3 x cubed plus 1/2 x squared plus some arbitrary constant. But I've put in a bunch of different arbitrary constants. So when the arbitrary constant is 0, then the curve that's actually passing through the origin is probably the one that is. Or if the arbitrary constant is 1, that thing is shifted up 1 unit. If the arbitrary constant is 2, it's shifted up 2 units. So all of these are graphs of the antiderivative, but shifted up or down a certain number of units. Now, this number of units is integer based, but that's not a requirement. This could be every 1/10 of a unit or every 100th of a unit. It's defined everywhere, but just used integers for simplicity. But here's the thing. Suppose we know some particular value that exists on the original graph. So some xy value that exists. So it exists on the original function capital F of x. So whatever that point is, let's say it's this point right here. All right, 1 and I don't know, 3 point something or 2 point something, who knows. Whatever that point is, only one of those curves is going to pass through that particular point. So what we do is we find this one function, which is known as a particular function. I should use a different color to highlight it. This is a particular function that solves that initial value. And there's only one particular function out of this group of possibilities that does that. Right? So, for instance, let's say that the point we know is 1.5 and 6. So if the point is 1.5 and 6, there is that point, right? It's located right here, 1.5 and 6. This is the only curve out of all of these that passes through that particular point. So that's what's known as a particular solution, or sometimes these are called initial value problems, but that's what's being determined here. Now, since you know how that works, let's go through and do a problem together so that we would actually come up with the solving, so you know how to solve for these as well. Suppose we have the function f of x equals 3x squared minus 2x, and we know that its antiderivative passes through the point -1, +1. Find the particular solution for which this occurs. So the first thing that we have to do is find the general solution. So this is the part that involves finding the antiderivative, tacking on a plus c in the end. Right, so the antiderivative, capital F of x, is going to be the antiderivative of 3x squared minus 2x dx. when I go through and find the antiderivative, it would be 3 times the antiderivative of x squared, which would be x cubed divided by 3, minus 2 times the antiderivative of x, which would be x squared over 2 plus c. Here the 3's cancel and the 2's cancel, so my general solution is x cubed minus x squared plus c. So every single antiderivative is going to have this form, but we want to find the particular solution, the one particular solution that passes through negative 1, 1. So to find the particular solution, here's how we do it. So we have the point negative 1, 1. This is an x value, and this is a y value. Y values come from plugging numbers into functions. So for instance, I could say, since capital F of x is equal to x cubed minus x squared plus c, I can say that I'm evaluating this function at the point negative 1. So that would be negative 1 cubed minus negative 1 squared plus c. But f of negative 1 is my y value. So that all is going to equal 1. So let's see. Negative 1 cubed is negative 1. Negative 1 squared is positive 1, but there's a minus here, so minus 1 plus c equals 1. So negative 2 plus c equals 1. And then if I add 2 to both sides, this cancels out and leaves me with c is equal to 3. So that means my particular solution that passes through this one point is going to be capital F of x equals x cubed minus x squared and plus 3. That's the one solution that passes through that particular point. And just to show you that this does work, here is the graph of the general solution. So I've taken the function 3x squared minus 2x, and I've had this program find the general solution to that and plot the general solution. So the general solution could be any of these particular curves. However, if we know that the point 1, negative 1 exists on this particular curve, 1, negative 1 should be, or it was negative 1, positive 1. So negative 1, positive 1 should be, let's see, my scale is strange, but it should be like that one right there. That should be my point. So let's see. If I solve the initial value, oh, I was right on. So there's the point negative 1, positive 1, and that's the curve that's passing through that particular point. And if you'll notice, the intercept here is 3. So that means I have my original function shifted up 3 units, which is why we found c was equal to 3. So this is, we solved for the one particular solution out of all these possibilities that would pass through that particular point.